Yeah, thanks everybody for joining. It's been a packed day of talks, and in my time zone, I'm in Central Time in US, so I've haven't been up as the start of the conference, but when I woke up, I have seen some sessions. And then today, I'll be talking about efficient communication between Python microservices using LavinMQ. And this talk will be in two parts. I talked a little bit about myself, but I'll dive in a little bit more. I'm a remote employee at 84 Codes, but I also go in a co-working space. I try to bike there, and I, and outside of work, I enjoy hiking and spending time outside, away, logging off, and away from devices. I also have a cat and a rabbit that occupies my time inside. A little bit about 84 Codes. The company has been around for 12 years now, founded in 2012, and we're a global company spanning offices Europe, US, New Zealand, Nigeria, and also Japan. CloudMQP is our SaaS offering where customers can create RabbitMQ and LavinMQ clusters. The primary protocol used on those is AMQP, Advanced Message Queuing Protocol 09.1, and MQTT. And MQTT is more used on IoT devices. LavinMQ is our open source broker that we created just a couple years ago from the ground up, and that'll be the focus of the talk today. This talk will be in two parts. Part one, diving into two concepts, microservices and message queuing, and ways you can use that for your microservices. And part two, go into an example application, and then it architected one way, and then that same application architected with microservices focus. Some of you may be already familiar with microservices architecture, but one of a good comparison is comparing it to monolithic architecture. In a monolith, services are tightly coupled, and all the components need to be there. It is written usually in one language. It's resides in one location. Starting a project out, this works great, and it's pretty simple to develop, maintain sometimes, and end-to-end testing is easy to set up as well. Monolithic architecture definitely has their places. However, the program will grow over time, and so does the complexity. Any changes you want to make will affect the whole system and require an extensive remake. And in addition to that, when a bug is introduced, the whole system may also inherit that bug as well. You can kind of see why developers look for alternate ways to architect their applications. This is where microservices shine. And that also has been an answer to a lot of drawbacks compared to monolithic architectures. The monolith here is tightly coupled. In contrast, the microservice here is loosely coupled and easier to introduce changes. And developers have the freedom to introduce new technologies as well, because those services are isolated. They can often try different languages or kind of in-flavor techniques. But with using microservices, there's something kind of missing at first. They reside on different servers and potentially different regions. They need to communicate with each other. What are the options for microservices to send messages to each other? At first, synchronous messaging may be a good solution. A microservice will interact with each other using a blocking interaction. In this case, the service needs to wait for a response. After the response, the service can continue. A typical example is using HTTP request and response interactions. The service will send a GET request from one service endpoint to another and wait for that service to respond before continuing. This may work at first, but it doesn't allow for the microservice to be autonomous. In the event of a single service failure, overall performance gets impacted as each synchronous dependencies between microservice arrays, the overall response time of clients gets worse. There is a solution using asynchronous communication using a message broker. The message broker sits between the services and facilitates communication between them. Message handling is outsourced to a separate service so that your services don't have to stop and wait for responses, and they can keep working in their own time. Also, creating the services, they all need to be configured to talk to that broker. They don't need to be configured to talk to hundreds or thousands of other services. Benefits of this include scalability, reliability. Using message broker is a way to achieve asynchronous communication. But let's look at how a message queue works. This is a basic example. Here we have the producer application on the left, and on the right, we have the consumer. In this case, a image scaling service, and the consumer can be anything as well. In the middle, we have the message broker containing the message queue. As the application, the producer sends more data, more and more users tend to add up, and they send only messages to the queue. They do not interact directly with the consumer application. Here, more and more messages are going through. Here, we're only showing a couple, but you can imagine that around hundreds or thousands of messages a second are being sent to the broker. The broker retains those messages. If the consuming application is not connected, it will hold those messages. Here, more and more messages coming through, more high throughput. The queue starts to build up. The consumer doesn't always have to be activated, which is great for if you have a very beefy machine sitting in the cloud. It doesn't have to be activated all the time. Here, now the consumer is activated, it starts to consume those messages. This is an image scaling service example. So it's just starting to run through that queue and crunch those images. And the queue continues to go down, and at the same time, the producer application can continue to send messages, helping with decoupling. But how does LavinMQ exactly fit into this? We developed out LavinMQ as an open source project written in Crystal. It is available on GitHub. And we've developed it completely from scratch. It is not a fork of an existing broker. We have been hosting message brokers for 12 years now, and we've made it extremely fast with kind of current architecture methods. Let's look at the inner workings of LavinMQ. So we've created this completely from ground up a few years ago, and like other message brokers, LavinMQ facilitates the exchange of messages between applications or services. And while doing this, messages are not lost between once they are sent to the broker and their messages are confirmed, the broker retains those. A concern with this is usually if the broker were to go down, but LavinMQ has solutions for this, which we'll dive into in a couple next slides. The image shows a typical use case. We have the producer sends messages to LavinMQ, in which the exchange lies, and then it routes the message to the queue. That's achieved with bindings. So the exchange is bound to a queue, and then it's able to look at the message. Depending on the exchange type, it can send that message to a single queue or multiple queues. Putting this in order, we have producer send the message to the exchange. The exchange receives the message and routes it to based on the exchange type with a topic exchange or a fan out. There are multiple exchange types. And then routing it will look at the message and the message header, routing key, and sends that message to the queue. Then the message reaches the queue, and then when the consumer is ready, it then gets the message from the queue, and that message has gone through from the producer to the message broker to the consumer. Let's look at how deeper dive into LavinMQ and how it handles messages. LavinMQ stores messages in what we call a message store, which is very clever naming. Similar brokers use also a similar method as well. As the messages, they are sent and they are written to segment files. And that are routed to queues in the queue message store. Messages are stored persistently on disk. This keeps messages safe. These messages are copied directly to the operating system caching layer without the need for syscalls, making the write a lot faster than if we were to cache messages in RAM, which requires us to make syscalls. Traditionally, other brokers cache messages within RAM due to the fact that they were created at a time where solid-state drives were not readily available. They were not cheap at the time. But with current advances in cloud costs and popularity of SSDs, we were able to make a broker that utilizes the benefits of those. At the time, other brokers, it made sense to cache RAM, but we've made LavinMQ to take advantage of the newer stuff. Here, we're going to dive into a little bit more how messages are consumed and also looked up through the broker. A routed message can be located in the message store with a reference from the queue's index to the message store. When a message is routed to the queue, the segment number and position in the segment are written to each queue's index. The queue index is just an in-memory array of segment numbers and file positions with some metadata. Routed messages are appended to the message store and also written to the queue index. Messages in the message store are then deleted when no queue index has a reference to a position in the message store. When LavinMQ starts up, it allocates memory mapped files for message segments using the mmap syscall. However, to prevent unnecessary memory usage, we unmap these and free up the allocated memory when they are not in use. When a file needs to be accessed, we map it again with mmap and use memory needed for that specific segment. This keeps the memory footprint very low and allows LavinMQ to sustain a virtually unbound queue lengths. And to summarize this, message brokers and LavinMQ keep your messages safe, so it facilitates communication between your applications. Additional safety can be achieved with clustering. In this slide and previous slides, this only references a single node. And now we've made it to part 2. We're going to show an example microservice app as well as compared to a monolith. And then we're going to show that from the monolith as a decoupled microservice. The application we're going to show is a Slack bot utilizing ChatGPT. With this application, users can mention the Slack bot in Slack, with text, and then it sends that text to ChatGPT and returns that response. And also, you can interact with the bots through direct messaging or in an existing channel. Here's an example here where communication's happening in Slack and someone's asking a question. They're utilizing the bot and then having the bot list steps for the other user. There's the response there. Let's look at how this application may be architected as a monolith. Here, the Slackbot GPT app receives messages from Slack, and then it also facilitates that communication to ChatGPT, receives that data back, and then sends it back to Slack. With this, there's it's a monolith. It's handling all the tasks we needed to. And utilizing this, you can use Bolt Python library, which is great for creating Slack bots. And then if you need to use this for other chat applications, there are some other technologies available. There's the app called Python framework called Airbot 2, if you would like to use this for Discord or even other messaging services. For this application, there are some scalability concerns. Slack itself has millions of active users daily. And if you were to create this app and have it available through like a marketplace as opposed to internally, if it gets popular and you're handling hundreds of thousands of requests a second, especially also trying to keep in track what peak times there are happening as well with this application. Asynchronous Python is able to help with this a little bit. We have some libraries as well: async Python, async.io, and asynchronous input output HTTP. As this is architected as a monolith, there are some concerns with this. The modules talk directly to each other within that server. If that server were to go down, then the whole service is lost. Because the components rely on each other and very closely, they are not exactly fault tolerant. Scalability becomes a concern as well, and performance is a major consideration. As it is a monolith, it is limited to the hardware that it resides on. And let's look at how this may be architected as a microservice. This will offer some additional benefits. Here, the application is broken into the Slackbot service, and then it's broken into process bot service. And for this example, there's just two part of this, but in real world applications, it could be hundreds of thousands of microservices that need to talk to each other. Same way as the monolith example in Slack, the message is sent to the Slackbot service, and then the service sends that to the processing bot, and then that facilitates communication with ChatGPT via the API. And there could use this for synchronous methods if you wanted to use HTTP requests, get and post. But as there are more users, the scalability becomes a concern while using a asynchronous method. So we have a use case for LavinMQ, our message broker. This replaced the REST API calls between the applications. Here, these services are decoupled. The Slackbot service does not need to directly communicate with the processing bot service. So if the processing bot service is down for any reason, the Slackbot service can continue to send messages to the queue in LavinMQ, and the queue can build up. And when the consuming service is ready, it can be then consume those messages. There are benefits to this as well, like scalability is a major piece. Here we have the Slackbot service, kind of representing an influx of messages and requests coming through Slack. So if there's, right at start of the day in a particular time zone, there we see a lot of traffic. We can spin up more services to handle those requests. And on the other hand, if there's still a lot more messages to be handled, the processing bot can be scaled up as well, depending on demand. That example just shows a pretty basic application, and only utilizing kind of two main services. In real life, though, there's going to be hundreds or even thousands of services that need to communicate with each other, spanning across IoT devices, mobile, and traditional desktop users. And also sometimes a single request needs to be used by multiple services. But I mean, and how do we achieve that? Here we have just we're drawing the lines in between. Mobile user that needs to interact with different pieces of the application. Oop. Sorry, I switched my targeted window. Here, the message broker is able to help with that. It will handle hundreds, thousands of connections and handle all those messages. So if for example, if the product service and inventory, they need the same message, the broker can then put those messages in multiple queues that it's bound to. And yeah, for this, the broker, again, facilitates communication between user applications and consumers. And let's see. Yes, making sure I don't have anything else for this. You can find this application as an example on our LavinMQ webpage. And we also have a Slack channel available as well for the message broker. So if you're just starting a project, if you have questions about LavinMQ, the Slack channel is there to help. Thank you for your time and looking forward to more talks. Does anybody have any questions?